speaker is Fernando Serna. He's going to talk about meson distribution amplitudes from base of Peter wave functions. Please, Fernando.
The lights. Hello. Okay. First of all, I would like to thank the organizer for giving me the opportunity to participate in this very nice workshop, and also to the sponsor for the support. My name is Fernando Serna. I am from Colombia, and today I'm going to talk about meson distribution amplitude from Bethe-Salpeter wave function. Well, all that I'm going to share today is in collaboration with these people here: Bruno, Eduardo Rojas, Javier Cobos, Roberto Correa. And this is basically the outline of my talk. First, I'm going to give you some motivation of why we are interested in computing Lycon distribution amplitude. Next, I'm going to introduce non-perturbative continuous tools, which are needed for the calculation of Lycon distribution amplitude. And after that, I'm going to present, I'm going to show you how we can use these non-perturbative tools to extract distribution amplitude. And then I'm going to present results for the case of pseudoscalar and vector meson distribution amplitudes. And finally, I'm going to talk a little bit about work which is in progress. Then I'm going to give some conclusion, and then I will stop. Well, hadronic distribution amplitude were introduced 40 years ago, and these distributions are important non-perturbative input for flavor physics. For instance, QCD factorization involves matrix elements with convolution integral. As you can see here, this integral is over a hard scattering kernel and the Lycon distribution amplitude. And here, while the hard scattering kernel is perturbatively calculable, the Lycon distribution amplitude only can be extracted from non-perturbative methods. And the interest on this Lycon wave function stems from the K-ball calculation in QCD factorization, which only employ the asymptotic form of this distribution. Today, we know that this distribution amplitude don't have this asymptotic form. Distribution amplitude enter in numerous of hard exclusive scattering processes. For instance, the pion, electromagnetic, and transition form factors. And a Lycon distribution amplitude is in quantum field is the nearest in quantum field theory to a Schrödinger wave function in quantum mechanics. And it is a probability amplitude that describes the momentum distribution of a quark and an anti-quark in the bound state valence focused state. Distribution amplitude are scale dependent quantities, and for instance, in QCD, the leading twist Lycon distribution amplitude for a pseudoscalar meson is defined via a meson to vacuum matrix elements in this way, where in this matrix element, this Fm is the pseudoscalar leptonic decay constant. This N here is an auxiliary light like for vector, and this W here is the Wilson line, which is necessary to produce a gauge invariant quantity. This matrix element can be expressed as the projection on the light front of the so-called meson Bethe-Salpeter wave function. And after projecting onto the light front the meson Bethe-Salpeter wave function, we can obtain the Lycon distribution amplitude. Here, this gamma is called of the meson Bethe-Salpeter amplitude that we can obtain from a bound state equation, and this F here is the dress quark propagator. Of course, all these objects here are no perturbative quantities, and in order to compute Lycon distribution amplitude, we need a no perturbative tools. Well, by using the same principle that in classical mechanics, in a given quantum field theory, we can derive the analogous to the Euler-Lagrange equation. They are called, but for green function, and they are called Dyson-Schwinger equation, and they are the quantum equation of motion. It is important to mention here that Dyson-Schwinger equations are an infinity many couple of equations, and they are a continuum method because we can answer to both the ultraviolet and infrared regime. And because we have an infinity many couple of equations here, we need a truncation scheme in order to have a treatable problem. Another important thing is that Dyson-Schwinger equation capture two emergent phenomena in QCD. Dynamical chiral symmetry breaking, which is the non-perturbative, the relativistic phenomenon responsible for the 98% of the visible matter in our universe, and also confinement. And these emergent phenomena are connected. And how this Dyson-Schwinger equation look in quantum chromodynamics? Here, this is, for example, the Dyson-Schwinger equation for the quark propagator, which is given by this equation here. This is the diagrammatic representation. This first term here is the the inverse of the Baire quark propagator, and this second term is called the quark self-energy, which introduce quantum correction. The main ingredients of this Dyson-Schwinger equation are the quark-gluon vertex and the gluon propagator. And it is important to mention that both the quark propagator and the quark gluon vertex that also have their own Dyson-Schwinger equation. And as a consequence, we have here an infinity many couple of integral equations. The general solution of the quark propagator is given in terms of two Dirichlet functions, A and B, or also can be written in this way in terms of the quark mass function, which is all defined by a ratio of the B function and the A function. Well, and this is, for instance, the Dyson-Schwinger equation for the gluon propagator. Tomorrow we will have a talk from Christine Aguilar. She's more expert in this gluon Dyson-Schwinger equation. And the important thing here is that in this equation, you can see another green function, which also have their own Dyson-Schwinger equation. For instance, we can see here the ghost propagator, which also have its Dyson-Schwinger equation. And then as a consequence, as I said, we have an infinity many couple of integral equations. And then in order to have a treatable problem, we need truncation, but this truncation is not arbitrary. We have to preserve symmetries of the theory. I'm going back later in this discussion. And for bound state, to obtain the Bethe-Salpeter amplitude, we have, for meson, we have the Bethe-Salpeter equation. And in this equation here, this is the fully amputated, this K here is the fully amputated quark and anti-quark kernel. And this F, as I said, this F is the quark or the anti-quark dress quark propagator. And the general solution of the Bethe-Salpeter equation will be depend of the meson the meson channel. For instance, for the case of the pseudo-scalar meson, we will have a 4 scalar function and 4 Dirac covariant. And this is the general solution for the case of a pseudo-scalar meson. For instance, for a vector meson, the situation is a little more complicated because the quantum number of the vector meson, we will have H Dirac covariant and H scalar function. Well, as I mentioned, we have a Dyson-Schwinger equation and an infinity many couple of integral equations, and then we need truncation. And the truncation must preserve in QCD the axial vector Ward-Takahashi identity. That will ensure that we will have massless pion in the chiral limit. And the simpler truncation that we can do is called rainbow ladder truncation. The rainbow truncation is for the case of the Ward propagator, and here we only employ the bare structure of the Ward gluon vertex, and we use an effective interaction for the gluon dressing function. And after analyzing the axial vector Ward-Takahashi identity, this is the kernel that we construct that preserve the chiral symmetry. And this is basically the rainbow ladder truncation. Now we have to specify what is the effective gluon interaction. And an interaction ansatz that has been proven its merit in the description of the phenomenology of the baryon and meson can be written as a sum of two terms. A first term is for the infrared part, and a second term is for the ultraviolet part, which will dominate a large momentum. And for the case of the infrared part, there are two models, two famous models, the Maris Standard model and the Kim-Chan model. And in practice, in our work, we use the interaction ansatz that reproduce lattice QCD result and Dyson-Schwinger equation, Dyson-Schwinger result for the gluon dressing function for the case, which implies that we will have a dynamical match in the infrared. Well, after solving the quark Dyson-Schwinger equation, for instance, for these different flavors of quark, we got the results. This result here is for the inverse of the A function, and just look at this plot here for the quark mass function. And from this plot here, we can see how a light quark is transformed into a massive quark in the infrared. And this is because the gluon interaction that is important at low momentum. And even for a zero quark mass in the QCD Lagrangian, a constituent quark mass is generated in the infrared. And this is dynamical chiral symmetry breaking. And what about confinement? Because the analytical structure of the quark propagator, we know that for a free particle, we will have a pole in the real axis. But for a confined particle, the interaction moves the mass pole of the axis. But this is not this is only a prescription of confinement. This is not a solution of confinement. This is because the analytical structure of the quark propagator. Well, in order to compute the meson masses, we need to know the solution of the quark propagator in a parabola on the complex plane, which is this parabola is defined by this q eta squared. And the size of this parabola is determined by the meson mass. And this parabola is fully defined when the meson mass and this eta parameter are known. This eta parameter is an arbitrary parameter which enter in the loop integral in the Bethe-Salpeter equation. And this is the momentum. This is the amount of the meson momentum that we can give in the loop integral. And due to the analytical structure of the quark propagator, a complex conjugate singularity, maybe inside in the integration domain. And this is a problem, and this has to avoid this. And for the simple case of the pion, where the mass is less than 1 GeV, this complex conjugate singularity will be outside the integration domain. This is my parabola, my integration domain in the Bethe-Salpeter equation. And as you can see, there is no complex conjugate pole. And the propagator functions are analytic, and it is possible to apply Cauchy theorem. However, for the case of a heavy meson like a D meson, where the meson mass is larger than 1 GeV, this complex conjugate singularity may lie in my integration domain. And in order to avoid this, but because this is a problem, because I cannot apply Cauchy theorem, we have to adapt this parameter. We have to choose another value of this parameter to adapt the size of the parabola and avoid these complex conjugates poles inside my integration domain. Well, now I have the solution of the quark propagator in the complex plane, and now I have to plug in the Bethe-Salpeter equation, and we solve this equation as an eigenvalue problem. And we basically introduce an artificial eigenvalue, and this is just practical detail, technical detail. We expand the Bethe-Salpeter amplitude in terms of the Chebyshev polynomial and Chebyshev moment, and we write in this matrix form. And basically, to recover the original Bethe-Salpeter equation, we got a bound state when this lambda is equal 1. And basically, we solve this equation here. And in this plot, I show you the eigenvalue trajectory. For instance, for the ground state, there is a theorem that guarantees that the larger eigenvalue will be the ground state, and the nets will be the ferrous-sided state. And you can see here that, well, when this curve cross lambda equal 1, we got a bound state. And for the pion, we got the result. And for the ferrous-sided state, you can see from this curve here, purple curve, that this will cross lambda equal 1 for this value, for instance. Well, this is our result for the mass spectrum and leptonic decay constant. And as you can see from this table here, we got good results. But the problem appears when you increase the meson mass, because we will have problem. We have to be smart with these complex conjugates pole inside the integration domain. And as you can see, we have a good result also for the decay constant, but I said we had problem a little bit with the decay constant. But this is all that we can do with this simple approximation, this simple truncation. But along the meson masses, we also obtain the Bethe-Salpeter amplitude. This is, for instance, the result for the case of the pion, the dominant. Well, this is all for the amplitude for the pion. This is the dominant one for the case of the D meson. Well, we have all the ingredients to compute Lycon distribution amplitude, and but we can not use, because the fact that we are working in Minkowski space, we cannot use this equation, or we cannot make a direct calculation of the Parton distribution amplitude from this equation. But we can do. We compute, and the strategy is compute Mellin moment, and after computing Mellin moment, we can reconstruct the Parton distribution amplitude. And in order to do that, we use interpolation for the quark propagator. That means that we fit our numerical solution on the quark-Dyson-Schwinger equation in this complex conjugate parametrization. And for the case of the Bethe-Salpeter amplitude, we fit our numerical solution to a Nakanishi form. And then, as you can see here, this is like a free propagator here. This is some kind of the denominator that look like a free propagator, and then we can plug here, and we can do analytically, well, after Feynman parametrization, we can do analytically the integral over k after the Jesus variable. And this is, for instance, the reconstructor process for the case of the mailing moment of the D meson. And for the reconstruction process, for the case of a light meson, we use an Gegenbauer expansion, and for the case of the heavy light the heavy meson, we use an exponential form. And these are the result for the case of the pion and Kion distribution amplitude. And as you can see here, we reproduce early result for this distribution amplitude. That means that for the pion, we have here a concave function, which is also broader than the asymptotic one. And for the case of the Kion distribution amplitude, we observe the same, but in addition, this is no asymmetric function. We repeat x equals 1/2. And this is basically, here we basically reproduce early result for Craig-Robert and company. And this is our result for the case of the heavy light meson, for instance. And as you can see here, as we expect, for the case of the BU meson, we will see that a more asymmetry function, because here the larger valence quark, we will carry the amount of the momentum of the meson. And it's the same for the case of the DU, DX, and of course for the case of the eta B and eta C, we obtain a symmetric function, which of course will tend to the delta delta function in the infinity quark mass. Well, what about vector meson? Recently, we have a publication for the description of the fair calculation of the D star and DX distribution amplitude. And as I said, for vector meson, there is a more complexity in the Dirac structure of the Bethe-Salpeter amplitude, because we have H, there is no force, now we have H. Well, this is no problem in solving the Bethe-Salpeter equation. This is the problem in computing Lycombe distribution amplitude, because the complexity of this structure. Well, in the same way, we obtain the bound state masses, and as you can see also, we have a good result for the case of this vector meson, and also for decay constant. And again, we also have their Bethe-Salpeter amplitude. This is for the case of rho meson, and this is for D star. For the case of vector meson, we will have two distribution amplitude. We will have a longitudinally, and we also have a transversally part, and which is given by this expression here. And after computing in the same way that we did for pseudo-scalar meson, we had here, for instance, our result for the case of the rho meson, and there is a comparison also with early result of Dyson-Schwinger equation. This plot here is for the case of the phi meson, and here we compare also with recent lattice QCD calculation from the lattice-Parton collaboration. And we also compute the longitudinal and transverse Lycombe distribution amplitude for the key star meson. And we compare also con lattice QCD calculation, and this is the first results in Dyson-Schwinger equation approach for this K-star meson. And we compare also with lattice QCD calculation, and our results are in agreement in the sense that for the case of the parallel one, we have almost asymmetric shape, but for the case of the transverse, we have here an asymmetric form. And this is also shown by lattice QCD. And this is the point here that this is the first results for the K-star meson. And also, we compute for the J psi, which, as we expect, is an asymmetric function. And first results for the case of the D star and DS star. Well, now I'm going to talk about a little bit about a work which is in progress, which is related with light-cone wave function and quantum information. This work is in collaboration with Brunel Benitz, Professor Gaston Klein, and Ian Croet. And this is from Kepani talk. And we see yesterday that if we project the Bethe-Salpeter wave function onto the light front, we got the light-cone wave function. And from the light-cone function, we can compute everything. For instance, there is a relation with the Parton distribution function just by integrating over the transverse quark momentum. Also, we can got GPDs, PDF, TMD, where the inputs are the quark Dyson-Schwinger equation and the bound state equation. That means the Bethe-Salpeter amplitude. And as I said, we can project the meson Bethe-Salpeter wave function onto the light front. And this is, for instance, yesterday we also have a nice talk from Tobias, and we can compute the light-cone wave function for the parallel and anti-parallel heilicity of the meson. And from this, we can derive, for instance, two distribution, the leading twist TMD and the PDF. And I did the homework for the Pion. And this is the result, our result for the case of the light-cone wave function of the Pion. This is for the anti-parallel, and this is the parallel, and this is the TMD. And then after integration, the Pion TMD over this transverse quark momentum, we obtain the PDF at this renormalization scale. Well, beyond their interest for the study of the three-dimensional Landau-Scale hadrons, distribution amplitude also carry important information about the quark and anti-quark correlation that we can explore at the quantum level by the measure of their entanglement. And we can use, for instance, well, this is just a preliminary result. We can use, for instance, the definition of the entanglement entropy from the Von-Neumann definition. And here we assume that all information is encoded in the PDF. And then we can use this to compute entanglement entropy, for instance, for the case of the Pion. And what we want to explore? We want to explore how this entropy evolves as a function of the scale, and also how this entropy behaves when the coupling constant in the Gatt equation, bound state equation, decrease or increase. And then I did the homework, and this is just a very preliminary, very preliminary results for the Pion entanglement entropy. And what we do here, we modify this D parameter. This D parameter enters in the interaction, gluon interaction ansatz, and it is the strength of the interaction. And then we fit this omega to this value, that this value give me the ground state of the pion. That means the mass and decay constant. And what we do here is variate this parameter here and see how behave this entanglement entropy. And this, for instance, the vertical line here is for the case of the ground state, for the D value of the ground state. And from we can see here is that before this value, this is something like constant, and then because this cross this value here, and the entanglement entropy start to increase, and then now we don't know what this peak here means, but what is the effect in modifying this parameter in my Bethe-Salpeter equation? For instance, this will increase the bound state mass. And we can also guess that this peak here probably corresponds to the first-sided state. But I don't know. This is, as I said, this is just preliminary results, and we are working on it. And well, now some conclusion. We obtained good result for the mass spectrum and decay constant for pseudoscalar and vector meson. We have first prediction for the Lycon distribution amplitude of D and DS vector meson. We have now the J-psi distribution amplitude that can be really be used in diffractive vector meson production, which are of the interest of the experimental program of the Electron-Ion Collider. And finally, we are also interested in the study of the entropy of the valence distribution of the valence quartz in the pion. And that's it. Thank you.
Thank you, Fernando. Are there questions?
Hi, Fernando. You have a scale, scale.
Yeah.
How much your results depend of this scale?
How much?
Dependence of the scale.
But what?
Of mu.
But you mean how change the, for instance, the Parton distribution? Basically, there is no much change when you change the scale. For instance, you will have the same, practically the same result. No.
So this is probably kind of a stupid question. So you were showing a formula for entropy in terms of the Parton distributions, and said it's kind of related to something for von Neumann entropy. Of course, von Neumann entropy for a pure state is 0. And the proton I'd expect to be in a pure state, but the formula was interesting. My naive interpretation of it might be that when you have a Parton distribution, you have sort of an incomplete picture because you lose a lot of phase information. And the information theoretic interpretation of entropy I'm aware of is that it encodes the amount of information that's there for you to learn in light of the description you currently have. So could the entropy you've defined be interpreted as the amount of information in the proton that you don't know from the fact that you don't have phase information from the Parton distributions?
Well, at the moment, I don't know. But
Fernando, thank you for the talk. I have two curiosities. One of them, I saw that you separate the two components of the pion wave function, no? Light front wave function. Do you get the probability of each one? This is the first question. The second question is about the entanglement entropy. I don't know if I understand well what you define, but you could get eventually from data, né? Because you have the Parton distribution. You could even compare with data. So these are the two questions. Thank you.
Well, for the first question, can you say again?
So what is the percentage of spin up and up and down?
This one.
Yeah.
If you have the probability of each one, because in principle you have everything defined.
Well, in order to compute the PDF, we have to normalize.
Yeah, the normalization.
Yeah.
Each component.
Yeah.
How much is it?
No, I don't remember. Now I don't remember.
Okay. The second question about the entanglement entropy. If you have looked at the data. Yes.
No, this is the next step also.
I have a similar question about entanglement entropy. Can you interpret somehow maximum point? What kind of state or it represents? Can you give some physical picture or something?
Well, as I said, this is preliminary. I am only entering this world of quantum information, but at the moment we are trying to interpret this, but well, I don't know.
I think he's asking what part of the physics of the pion this is kind of trying to get information. I think on the valence part of the, and that's the reason it's not a pure state. No more questions? Okay, let's thank Fernando Tan.
Thank you.
Is this on? Okay, that's it. So next we have Adam Fritz. He's going to talk about something that I don't recall. Let's see what is.
Should also put a timer here to make sure I stay on time.
Yeah, you have plenty of time because
Okay.
he finished a bit earlier.
I'll set myself a timer anyway.
You can take all the time. Okay, electron time and the rest frame structure of hadrons.
So I'm going to talk a bit about how information that is extracted from the EIC in the future could possibly be interpreted in terms of the spatial structure of hadrons. So is this my pointer? Yeah. So the basic idea is that various sorts of form factors, this includes electromagnetic form factors that we already have from experiment, but also the gravitational form factors, which we very hopefully will be able to get from the EIC. These are extracted from experiment and in principle encode some sort of information about the spatial structure of hadrons. To a certain extent, the relationship between these form factors and the spatial densities is kind of controversial. Increasingly, I've been thinking that it's maybe something that shouldn't be seen as a controversy, but something where there are a bunch of alternative perspectives on how to interpret the spatial structure of hadrons that perhaps complement each other in certain ways. So there are a variety of perspectives. There are these so-called bright frame densities, light from densities. There's recent work by Yulia Panteleva and her collaborators doing localized wave packets in 3D. There's the work of Cedric Lorset and his collaborators using Wigner phase space formulations. I believe he'll talk about that tomorrow. There are these multiple moment densities that Yang Li and his collaborators came up with more recently, which honestly I think is an especially elegant approach, but he's not here to talk about that, unfortunately. I won't solve that controversy or comment on the controversy here. I'll just say that there are a variety of perspectives, and I'm going to focus primarily on light front densities. In particular, a new conceptual framework for thinking about light front densities in which they can be interpreted as rest frame densities instead of infinite momentum frame densities. Before actually starting with the meat of the talk, I want to emphasize that the talk is about phenomenology. You get these form factors from experiments somehow. Perhaps you can get them in a model or from lattice. And then you do Fourier transforms based off of the arguments in this framework. So I'm not necessarily arguing for using light front quantization. That's kind of a controversy I don't want to get into. So you all know what light front coordinates are. They're a different foliation of space-time. Your transverse coordinates remain the same, but you define a new synchronization convention. So you define your planes of simultaneity differently than in Minkowski coordinates in terms of what is called x plus. And you also redefine your spatial grid by using x minus instead of z as a spatial coordinate. I do want to dwell a little bit on what changing your synchronization convention means. Traditionally in Minkowski coordinates, you use what's sometimes called the Einstein synchronization convention, sometimes on Einstein-Poincaré, in which if two spatially distant observers have clocks that they want synchronized to each other, Alice might send a light signal to Bob asking the current time. Bob immediately sends a light signal back with his current time. Alice sees that there was a time delay, assumes that the time delay for the signal going in both directions is the same, and synchronizes her clock accordingly so that it's a certain amount of time ahead of the time Bob reported instead of exactly at the time that Bob reported. Light front synchronization is basically doing this a little bit differently. Instead of saying that the time delay was the same in both directions, if Bob is located exactly in the plus z direction from Alice, then Alice takes whatever time Bob gave her and says, okay, I'm synchronizing my clock to that. That's the current time. So slices of fixed t plus z are considered slices of fixed time, and clocks are synchronized accordingly. This, of course, does not contradict special relativity at all. Relativity and Lorentz covariance requires only that the round trip speed of light from a point to somewhere else and back is invariant under Lorentz boosts. The convention that the one-way speed of light is the same in all directions is actually a convention. It's a stipulation or a definition and not an empirical fact. And Einstein points this out several times in his original paper. And in fact, redefining time coordinates amounts to just changing this definition. That includes using light front time. And there have been a lot of papers talking about this in technical detail. There's a very nice long review by these folks that you can read here. They tell you how to do Lorentz transformations, electrodynamics, and so on in an arbitrary synchronization convention. And there's a nice YouTube video talking about this by Veritasium that came out a couple of years ago. Another neat aspect of choosing to use light front time instead of the Einstein synchronization convention is that what you identify as a pure boost leaves transverse images invariant. And the reason for this is related to an optical effect called Terrell rotations. In your traditional Minkowski coordinates, if you boost an object, it becomes length contracted. That's simply a fact of how Lorentz transforms work. However, if you, an observer, look at an object that's transverse boosted with respect to your line of sight, it doesn't look contracted. The contraction, the 1 over gamma factor is there, but it also takes more time for light from the far side of the back to reach you than the near side of the back. And as a consequence, the back of the object appears drawn out. And in fact, the length of this drawn out back looks something like square root of 1 minus 1 over gamma squared. So there's something that looks like a sine-cosine relationship between these factors. And in effect, the objects appear boosted. So instead of length, if these die are stationary and these are the same die moving at an oblique angle with respect to your line of sight, they appear rotated, you see the back of them. But that's for what you call a transverse boost in ordinary Minkowski coordinates. In light front coordinates, a boost is changing something with respect to light front time. Light front time is t plus z, so you need to combine a t derivative with a z derivative, so you actually have to do a counter rotation. The counter rotation cancels out the Terrell rotation, and the end result is if you do something that can be called a pure transverse boost at fixed light front time, the object looks invariant. It looks exactly the same as before you had boosted it. At least in the approximation that's exactly in front of you, exactly in the plus z direction, and it's small enough that distortions due to the fact that things are coming out at different angles can be neglected. As you can see, these are also a little bit warped in addition to just being rotated, and that's because of the transverse size. I'll be neglecting those effects here. So one slide that I've liked to give a lot over the past few years is to say that using light front coordinates is not the infinite momentum frame. You redefine your momenta and your coordinates in a very peculiar way, but all of the momenta are still finite. And we didn't do a Lorentz boost to do this coordinate transformation. However, I have to eat some words that I've given in previous talks. Light front coordinates don't really give you a rest frame either. They're not the infinite momentum frame, and they don't define a rest frame. And the reason is that the x minus coordinate is a very weird spatial coordinate, and your grid of spatial coordinates is not Cartesian. So I want to do a little tangent into what we mean by reference frames, or at least what I think we mean by reference frames. I would consider a reference frame to be a hypothetical grid of spatial points that can be used as reference for giving you spatial coordinates. If you want to think of a space-time grid, you'd also attach clocks to all of these points and synchronize them in some way or other, whether it be through Einstein synchronization, light front, Eddington, or some other synchronization scheme. But I wouldn't consider the synchronization scheme to be part of the frame. I just consider the frame to define the spatial coordinates. Nonetheless, with light front coordinates, your spatial grid is different than your Cartesian grid in Minkowski coordinates. In fact, if you were to look at a point of fixed x minus, that would mean t minus z is fixed. So this point is moving at the speed of light with respect to what you would consider a Cartesian grid. So you can think of light front coordinates as furnishing a collection of light speed frames, which is a little bit weird and doesn't really give you access to rest frame descriptions of objects. So the nice thing about light front coordinates is that you have this x plus coordinate. It's related to something called the Galilean subgroup, which I'll get into in a few slides. But x minus prevents you from getting a rest frame description of hadron structure. So I guess the question I have is, why not just use x plus as the time coordinate and z as a spatial coordinate? And actually, some folks thought of that over 20 years ago. Jerry Miller, Matthias Burkhardt, and I forget the other author's first name, Blundin, the first author, thought of using this coordinate system, use light front time, but then ordinary Cartesian spatial coordinates, originally in the context of solving some toy models for potentials that are a function only of space. But this is very useful for densities too. It allows you to use light front synchronization, so you get a time variable that's invariant under the Galilean subgroup of the Poincare group. And it also allows you to use ordinary Cartesian coordinates, which allows you to furnish a description of hadrons in their rest frame from the point of view of someone who's at rest with respect to the hadron. There are, of course, downsides to anything that might seem nice. You get a very weird metric, a very weird inverse metric. Your 4 Laplacian and your invariant proper time element both have fairly strange forms, and you have to be very mindful of raising and lowering coordinates. Momentum and velocity can be a little bit weird here too. At a basic level, I would consider energy and momentum to be those things that generate space and time translations through these basic commutation rules with an operator. Defining them this way gives you an on-shell dispersion relation that is quadratic in your perpendicular momentum, much like with ordinary light front coordinates. The components of your energy momentum, your energy is actually the same quantity as in instant form coordinates. So it's what you traditionally think of as energy, which is pretty neat. And the z component of your momentum is identical to what you'd call P plus in light cone coordinates, which is also kind of interesting, especially since that this is the momentum variable that shows up in parton distributions. You get very weird formulas for the velocity, though, especially the z component of velocity. Very unusual formulas. But these velocities, when you set them all to 0, give you a system that's really at rest with respect to your Cartesian coordinate grid. Because you're doing time synchronization differently, your Lorentz boosts have somewhat different formulas. The neat thing here is that your transverse boosts leave your time variable invariant. That's something that is really convenient for working with a spatial density description. Your longitudinal boosts, however, don't. They either cause time dilation or time quickening, depending on the direction of the boost. In particular, if you boost the system so that it's moving towards you, its clock will appear to run faster from your perspective, and also the length of it will appear contracted. If you boost the object so it's moving away from you, its clock will appear to be running slower, and lengths will appear to be longer. And these are basically relativistic blue shift and red shift. You're taking something that traditionally you would think of as only apparent, something you'd calculate as what an observer is seeing, and instead choosing in this coordinate system to say, that's what's happening. So I mentioned the Galilean subgroup a couple times. I probably should have given this slide earlier since the Galilean subgroup is really important. It's simply a group theoretic fact that the Poincare group has a 2+1 dimensional Galilean subgroup. And in fact, the time coordinate in this tilted coordinate system and the transverse spatial coordinates transform like time and space under this subgroup. What we would call PZ in this coordinate system, which is identical to P plus in traditional light front coordinates, is a central charge of the group, meaning that it remains invariant under all the transformations in this group. Time is also, I did mention time is invariant. Anyway, so you basically get a fully relativistic picture in terms of 2 of the 3 spatial dimensions that looks a lot like non-relativistic physics with PZ instead of M. And in fact, you get something that looks like Newton's force law, quadratic dependence on perpendicular momentum, a velocity momentum relationship, and so on, that look very familiar from a high school physics course. So the reason that the Galilean subgroup is relevant for spatial descriptions of hadrons is that if you integrate out your remaining coordinate, the one where you don't have this nice non-relativistic looking description, that basically forces your initial and final state to have the same PZ and thus the same central charge. And because of that, you end up getting that any matrix element of a local operator can be decomposed into something that depends only on the central position of the hadron as a whole, smearing out an internal density that is independent of the wave packet that the system is prepared in. So you can interpret this as an internal density. This smearing function is something that in the simplest cases would just be the square of the wave packet, and in more complicated cases will involve derivatives of the wave packet. And the argument of your internal density is just the position you're probing minus the central position, so an impact parameter. And the fact that this is the argument that pops up in there is actually due to the fact that that's invariant under light front boosts. Otherwise, you would need some sort of Lorentz transformation factor inside of the internal density. Before showing density results, I also want to give another little tangent into which component of the form current you would consider to be the charge density. So when we say charge density, since we're working at fixed light front time, we mean the density of charge over a hypersurface of fixed light front time. So if you were to draw on a TZ axis, it would be this diagonal here. The density needs to be something that if you integrate it over all of space will give you the charge, and it needs to obey a local differential continuity equation. And the quantity that satisfies this would be what you'd call J0 in the tilted coordinates, which in terms of ordinary Minkowski coordinates is J0 plus J3. In other words, J plus, which is what folks working in light front coordinates call the charge density. So this isn't something that we just choose to call the charge density because it's convenient. It actually is the object that has all the properties of a charge density in this coordinate system. And because of the Galilean subgroup again, you have a really simple formula for the internal charge density. You just take your quantum field theory operator and sandwich it between momentum kets, and you can do this for any spin state. Divide by 2 times p plus, and take a 2-dimensional Fourier transform. And you end up in terms of your empirical electromagnetic form factors getting transverse densities that look like this for the proton. This is using parameterization due to J.J. Kelly. For longitudinal polarization, you get this nice little profile that is azimuthally symmetric. For transverse polarization, it's kind of hard to see, but this is a little bit lopsided. It's a little bit more dense on the right than on the left. This is a lot more pronounced for the neutron. If you look at the transverse neutron density for longitudinally polarized state, it appears to have a negatively charged core surrounded by a diffuse positive cloud. This was found already by Jerry Miller in 2007. And if you look at a transversely polarized neutron, transverse in this case spin up, so spinning this way, it appears to have something like an apparent electric dipole moment, apparent being the key word here. So why do these modulations happen? There are traditional descriptions of this as being a kinematic effect due to boosting to the infinite momentum frame in order to work with light front coordinates. However, if you derive this description in terms of tilted coordinates, you never have to boost to infinite momentum. You have a description that is invariant under boosts and a description that's valid in the rest frame since tilted coordinates are in terms of the ordinary spatial grid and thus can describe a system at rest. However, there are still kind of wonky things going on if you use tilted coordinates. And the argument I want to make is that these azimuthal asymmetries, this apparent electric dipole moment, is an artifact of basically optical effects, which within a description using fixed light front time, you bake into your formalism. In fact, this was already known in the late 1930s. George Gamow published a series of popular articles about Mr. Tompkins in Wonderland, and he uses the relativistic wheel as one such peculiar optical effect. So imagine you have a static wheel with regularly placed spokes. Now you want to compare to a spinning wheel. The wheel a little bit oblique to your line of sight so that the rim isn't blocking the spokes, but also so that some of the spokes are turning towards you and some of them are turning away. The spokes moving away from you are redshifted and appear to move slower. Because they move slower, they start piling up. The spokes that are moving towards you appear to move faster and get around to the bottom of the wheel faster. And the result of combining both of these is that the spokes appear to be denser on the side of the wheel that is moving away from you. These same distortions should be present in anything that is stationary and spinning. And in the light front formalism, or the tilted light front coordinate formalism, you're taking optical effects such as this and considering them to actually be part of your density. So this should be happening in the nucleons too. So if you do flavor separation, assume that the proton and neutron are just made of up and down quarks, take the right linear combinations to get each distribution. The up quark density in the proton looks like this. It's a little bit lopsided towards the right. And if you look at the longitudinal current, it appears to be moving towards you. Purple here means towards and green means away. Towards you on the left side and away from you on the right side. So the fact that this is lopsided towards the right is compatible with the heuristic from the relativistic spinning wheel. If you look at the down quark density, it's a lot more lopsided, but in the opposite direction. And if you look at the longitudinal current, it is moving away from you on the left and towards you on the right. So the charge density is lopsided in exactly the same way as you would expect from the relativistic wheel example, from the spokes piling up in the direction that's moving away from you. You could also go a bit further. This is admittedly a very silly slide because the proton is not a rigid wheel. It isn't things orbiting in circular orbits. But if you were to roughly kind of say that we have a toy model along those lines, you'd expect the up quarks and the down quarks to be orbiting around the proton with angular frequencies like this, with the down quarks orbiting in the opposite direction of the proton spin and the up quarks orbiting in the same direction. Of course, this is a super simplistic model, so these numbers should not be taken too seriously, but it's kind of a toy illustration of how these effects can be explained entirely as due to relativistic optical effects, and it's not necessary to boost your system to infinite momentum in order to see these. Now, I talked about electromagnetic densities, and the thing that's really interesting for the EIC is that if you do hard exclusive reactions, you try to extract GPDs, from taking millimoments of these, you can get gravitational form factors and get access to the EMT. There's already a lot of very good work done on three-dimensional energy momentum tensor densities by Cedric Lorset, Yulia Panteleva, Maxime Polyakov, Peter Schweitzer, and all of them. More recently, there has been some work on light front densities of the energy momentum tensor. But one place that light front densities have always struggled a little bit is that a lot of the meaning of a lot of components of the energy momentum tensor weren't clear. And one of the nice things about using these tilted light front coordinates, using z instead of x minus as a spatial coordinate, is that if you write your energy momentum tensor in a mixed way, upper and lower components, then all 16 of these have a clear physical interpretation. You have an energy density, 3 momentum densities, 3 energy fluxes, and a 3x3 stress tensor. This is currently a work in progress. I do have a lot of time left, so in principle, I could talk a little bit about some of the work I've been doing to calculate that. Unfortunately, it will be less entertaining than the first part of the talk since it's largely just formulas. I'm not sure how eager all of you are to get to your coffee break. Should I go on and talk about these formulas? All right. So the energy momentum tensor is a lot harder than the electromagnetic forecurrent. You still want to, right? You have this EMT operator sandwiched for some physical state, integrate out the longitudinal coordinate, the problematic one, and you have a smearing function that contracts with an internal EMT that you want to also consider your rest frame EMT, and you have this transverse impact parameter that's invariant under light front boosts. Now, how do you take what you get on this side and separate it into the smearing function in the internal density? That's actually ambiguous. In fact, it was ambiguous for the electromagnetic forecurrent before, but when you actually go and calculate out all the structures, it's intuitive enough to kind of eyeball it and say, I think this part is internal and this part is a smearing function. It's especially obvious in something like a spin zero target electromagnetic densities because it literally just becomes your 4 probability current smearing an internal charge density. But as an example of such an ambiguity, you could say, okay, I absorb a factor 2 into here and 1/2 into here. And if this is a sum of several terms, you can absorb different factors between the different terms, and just eyeballing this, it wasn't clear at all. So the difficulties have come from needing to define a fixed scheme for separating the smearing functions and the internal densities. So the thing I've been working on is to kind of look at classical physics and first quantization for a heuristic. So if you imagine for a moment that the proton or the pion is a classical system that is stationary so that its rest frame energy momentum tensor has no time dependence, it only depends on your 3 spatial coordinates, then you might say that, okay, if I'm going to try to emulate quantum mechanics in some way, I have to introduce ignorance about things. I don't know how fast the system is moving, so there's an unknown Lorentz boost that I have to perform, and I don't know where the system is, so there's an unknown translation I have to perform. Then I have to have some probability density over these things that I integrate over with some measure for the Lorentz transformations, and I have some probability density. And is it possible to just first quantize this naive classical heuristic description? Is there some map from this thing here, Lorentz transforms and translations acting on some unknown function? That gives me a quantum operator that I can just trace along with my density operator and get something that looks kind of like the quantum field theory matrix elements. So first complication with that is I need to clarify how I'm going to quantize it. That is ambiguous because whenever you have classical operators in phase space, a lot of the time there are different quantum operators that give you the same classical quantity in the classical limit. So you need to pick a scheme and stick with it. While quantization seems to be a fairly popular one when working in the Wigner phase space formalism, so I just use that. One really nice thing about while quantization is something called McCoy's formula. If your objects obey the canonical commutation relations and you try to find a polynomial, or you try to write this out in terms of your x and p operators, the while quantized version can always be written as a sum of this sort with combinatorial factors and your x operator sandwiched by p operators to various powers. The reason that's nice is that if you then sandwich this between 2 different momentum kets, your p to the s, well, this says p to the r now. I guess I switched the r and the s. That's a bit of a mistake. Pretend that this says s and r instead of r and s. Your p to whatever power becomes your average p between the initial and final state to that power. So this is the same variable that appears in your Lorentz decompositions of local operators in terms of form factors. So it's a very nice property to have, and it's a very good reason to use while quantization. Position operators can get a bit tricky. If you're doing things at fixed light front time, your transverse position operators are very nice. If you look at them in the momentum representation, they're just like non-relativistic position operators. Of course, that's related to the Galilean subgroup and the fact that the transverse plane is so nice. If you look at your longitudinal coordinate operator in the momentum description, it is kind of wonky looking. It has an additional part that's kind of reminiscent of Newton-Wigner operators. So it's actually a non-local position operator. And in fact, if you try to do this whole thing here and you look at the way that this depends on your momentum variable and you look at the way your quantum field theory form factor decomposition depends on its momentum variable, these are inconsistent with each other. So the idea seems to fail. But if you integrate out your z coordinate, which is what you do for these fixed light front time densities anyway, the inconsistencies disappear. In fact, this dependence on the Lorentz transform inside of your naive rest frame EMT also disappears because your transverse impact parameter is invariant under Lorentz boosts. So you get something where the P dependence on both sides is consistent. Equals probably wasn't the right thing here because these are different objects from different models. Pretend that this is replaced by a new symbol that means compatible with. One last subtlety is how these Lorentz boosts depend on your momentum argument. In principle, your Lorentz boosts depend on the velocity that you're boosting to. And if you were to look at things classically in terms of tilted coordinates, it's clear enough. I showed you before that there's this perpendicular velocity, which is linearly proportional to your perpendicular momentum with pz as your central charge instead of m, but you have this longitudinal velocity that's actually a bit more complicated. So you might think, okay, replace little p with the big P that you're using as a variable and be done with it. And that doesn't work. And the reason that that doesn't work is that your classical momentum obeys a dispersion relation, but your big P is an average of two on-shell momenta that each obey the dispersion relation on their own. So instead, your big P obeys an alternative dispersion relation with this momentum transfer in here. And if you go to that there's no longitudinal momentum transfer, which is something that you force by integrating out z, then your effective mass, instead of being m squared, is m squared plus a quarter of your transverse momentum transfer. So the way that you get consistent momentum dependence between this naive quantized classical heuristic and the actual quantum field theory matrix elements is you plug these average velocities into your formulas for the Lorentz boosts. A very weird property of this is that quantum mechanically, if you want to define something that's at rest or at average rest in tilted coordinates, you don't use the classical relation, which in tilted coordinates would be that your momentum is 0, 0, m instead of 0, 0, 0. You would have to use that instead of m, this square root of m squared plus a quarter of the transverse momentum transfer squared. And as a peculiarity of this, if you use this scheme within tilted coordinates, nearly all of your transverse densities are actually different than your traditional light front densities. Charge density is actually an exception to this. Any corrections that you can get cancel out in the charge density that I showed you before is still exactly the same within this peculiar scheme. So using all of this, the way you can define your smearing functions is with these Lorentz boosts containing these average velocities. And the way that you define your internal density is with a, that should be squared instead of cubed, 2D Fourier transform with P set to the rest condition, which of course involves this 1/4 delta squared. This is just some equations. One thing I want to remark is that the energy density I get this way for spin 0 target instead of looking like the light front energy density, actually looks like Polyakov-Schweitzer's energy density projected down to 2 dimensions. So I think that that's a pretty neat finding. Shows a little bit of synergy between the traditional 3D approach and this approach. And I want to leave you with a quick calculation I did of the pion energy density in the traditional light front coordinates. It actually has a delta function at the origin, which I've widened a bit so you can actually see it on the plot. But this thing here is supposed to represent a positive delta function. And the light front, the tilted coordinate transverse density is kind of more mellow compared to the light front one. The benefit of the tilted coordinate density is it can be interpreted as a rest frame density. Anyway, that's what I have to say. Thank you for your time.
Are there questions?
Great talk.
Thanks.
Thank you. I can probably predict that when you extend your last work from the Eigen-Newton tensor to spin 1/2 or any spinning targets, you will have something different from Polyakov and
Yes.
Schweitzer. It works only because you have spin 0,
Yes.
and you're not affected by these Melosh-Wigner rotations.
Correct. I can also say that the energy density you get for spin 1/2 is different if you use the symmetric energy momentum tensor and the asymmetric one.
Are there more questions? Okay, if not, thank you.
Thank you for your time.
I think this was the last